x2 is in relation with x5. x5, is it in relation with x3?
No.
No. Okay, you understood. This one is in relation with this one. This one, can I say that this one is in relation with itself?
No.
No.
No, because, okay, so it's because of the convention. This one, is it in relation with itself?
Yes.
Yes.
Yes. So, what you should have is this. Now, I am able to prove with interval analysis that this one is in relation with this one because of some scalar product with the orthogonal, with a normal vector to this surface. I will be able to prove all this relation, okay? But I will not be able to prove this relation. I am not able to prove that this one is in relation with this one because I have no theorems for this.
So you can only prove relations between different sets, not the same one.
Yes, we have a theorem that tells you
different ones.
we have theorems.
But
In this, we have theorems that tells you that if I am here, and if I am not in relation with this one not a relation, this one is not a relation here, then this one is a relation with itself. So it's possible to prove it, but not here. Because we have not the theorems that make it possible with interval analysis to prove that we have here some limit cycle.
What if
We don't have.
what if this arrow on the left side was only in one direction, was only facing down? This one, yeah, this one was
This
only,
one?
yeah. If
This
it was
one?
only this
You want to understand this one? You want to understand this relation?
Yeah.
Here. Here, if I start here,
Yeah.
I go.
Right, but would it mean that if you go to the next slide, would it mean that you could actually prove that this area is in relation with itself?
Yes, we can prove that this one is in relation with this one, and this one is in relation with this one.
Yeah, but I mean, if situation was slightly different, if this relation was only facing down, if this
Facing down.
yeah,
See, if
In
there were
this
only
situation-
facing down, I would not have this row.
yeah,
But maybe sometime I'm not able to prove it.
yeah.
Here you can have, just to illustrate that sometimes I am able to prove the relation, sometimes not.
Yeah,
That's what I
I
wanted to
understand
say.
that the situation is
Here
impossible.
I'm quite lucky, of course, just an illustration. But it explains the complexity of the problem. So here I have some uncertain row, sometimes all of them are certain, except this one, in this example. Just do it. Yes?
One, I don't get why it's uncertain. And two, if it is uncertain, why don't you just bisect and prove that both of them?
Of course, you can do that. But I just want to illustrate what can happen in practice. I don't want to say that this decomposition is a good one. It's a good one to explain things. But of course, you have to bisect, you have to improve the algorithm. Me, at the moment, I try to find a simple example, a possible graph, one which is uncertain, because I want to illustrate different things. But of course, I could do better.
But why is it uncertain? This one.
Okay, which one? This one?
Yes.
Because if I want it to be certain, I need to prove that there exists an initial point such that I will always stay inside. So, with this, at this moment, I am not able to prove that there exists a trajectory which always stays inside. Okay? I'm not able. Maybe it's possible, but I was not able. The method is not able at the moment. We don't have a theorem for that. We did, but we don't. So there is. And I'm not able also to prove that for all x0, I will go out of x6. So maybe I am in relation with x6, maybe not. Okay.
X6 is a relation with X4. I mean X4 in the right side, yes?
Yes, it's the same as this one.
Exactly. But in the next picture, you didn't show one. See, between
No.
X6 and X4, there is no any.
No.
Yes.
X6 is in relation with X4.
No,
But this set and this set are the same.
Oh, so
Just a-
only you arrive for the one.
Yes, yes. When you, like when you look at the map of
Oh,
the
you don't
world.
need to everywhere that. Okay,
okay.
I get it. Yeah, yeah. I
Okay.
get it.
Okay, so now what I have is, what I have is this, a graph. X6 is here, X4 is here, it's only one set. I have a graph. Okay, what I want also to show here is a graph with a machine can be represented by a Boolean matrix. You know this notion? So when you have 0, it means that x1 is not in relation with x1, but x1 is in relation with x2. x2 is not in relation with x1. So I have a graph is represented by a Boolean matrix. When it is unknown, it is an interval, 0, 1. So it is considered as an interval graph or an interval Boolean matrix. Okay. So, of course, the graphs, the lattice, you can say that a matrix is smaller than another one, corresponds to a graph is smaller than another one. So it has an order structure. It is a lattice, so we can define intervals on this. An uncertain graph is an interval graph for us. Okay? Okay. So here, in my particular case, I just have one interval, but most of the time we have many intervals. Okay, understand? Now, I have this. What can I say about the convergence? What will be here the attractor of this graph? So what is an attractor of a graph? I take a point, I follow the arrows, and if I am able to come back to the node, then I say that it belongs to the attractor. You understand that? For instance, x5, this node, does it belong to the attractor?
No.
Yes.
Yes, you can
Because
go down,
those,
up, yeah.
those, and those. I come back. Okay? X3, it belongs to the attractor?
No.
X3?
X1, it belongs to the attractor?
Yes.
Yes.
Yes, because I go to X2, to X5, how can I come back?
You go to X6, go X4.
No, you can't.
No, you don't.
I can't. Okay. So how can I prove it? There is a very efficient algorithm for this to find attractor of graphs. I take I take all nodes that have only output arrows. So this one has an output arrow, no input arrow. So I remove them. Understand? This one I can remove it. No input arrow. Then, if I remove this one does not exist anymore. Then, this one can then be removed.
X1.
No, you can't.
No, I can't, excuse me. This one can be removed.
Yes, and then you move.
And then X3.
Because this one has been removed. Then I remove. Then, this one can be removed.
Yes.
And I will converge to this graph.
Yeah.
It corresponds to the attractor. So it can be done efficiently. But here I have also an interval graph because this one is 0 and 1. So how can I do in practice to implement this? I have a graph, I compute the transitive closure of the graph. Because what I have explained before, it is a relation. And if I want to compute the transitive closure, I have to compute a graph, so the matrix, plus the square of the matrix, plus the matrix over 3, So this graph, so if I have a graph, excuse me. Ah, yeah. C'est bon là. Bon instant. If I take a graph and I represent by a matrix, here, if I have a 1, it means that there is a path of length 1 between node E and node G. If I take G squared, it corresponds to the path of length 2. For instance, here,
Going through two nodes.
here, excuse me for technique, I have to find one which is good. If I have 2 arrows, for instance, this one and this one, then I can say that this one has a path of length 2 between this one and this one. And square G corresponds to all relation of length 2. When I compute here, it is the transitive closure will correspond to the path of length 1 and also the path of length 2, length 3, and so on. And since the transitive closure is monotonic, it means more I have 1, more I will have transitive closure, arcs for the transitive closure, it means that it is a monotonic relation. So I will be able to compute the transitive closure of the lower bound and of the upper bound, and here, in my particular case, I converge to a matrix, to a graph, which is not an interval graph anymore. So what I can say here, I can prove that the attractor is given by the diagonal, so 1, 2, 3, so x4, x5, x6, will correspond to this set. So what I was able to prove is that if I am here, I will converge to here. So this set is an attractor. No, is an enclosure of the attractor. This set contains the attractor. Okay? So I can prove here that I will enter inside the disk with a radius 7.6. Okay, but it is not because I am here in this disk that I will stay inside the disk. But one day I will enter inside the disk and I will always stay inside because I will never be. You understand what I mean? So what I wanted to show you is that interval analysis is a good tool for discretizing, to go from continuous problem like differential equation, nonlinear equation and with sine, cos, and to graphs or to the world of computer. Okay, so it was an illustration related to the study. Yes?
I'm not sure if you explained that or not, but how do you do the one? How do you select the areas?
Yeah.
X1, X2, X3.
I was just
Ah,
gonna
yeah, no, it's not, I don't know. I don't know. No, it was not, it's possible. It's possible. There is some possibility to, but I can say it's understood. At the moment, what I want to, in this example, I want a tool to prove something that was not possible before. But to prove it, I need the intuition of, it's not totally automatic, but it's a tool to help me to find the attractor. It's the same as the proof of Warwick Tucker. There is a lot of part of the proof that come from a good intuition of the problem. But the interval method is just here to help you to find the attractor. But I can say at the moment, there is no method able to find this decomposition. No method, of course you can find a method that does not work very well, but to me you cannot say that there exists an efficient method, a clever method able to find a good decomposition.
Okay, so some other question.
Yeah.
So you gave an example of 2D.
Yeah.
How does that scale to
Ah.
higher dimensions?
Impossible to say. Impossible to say. What I can say is that the methodology that is explained here, the theorem we have to prove work for n-dimensional problem, but it is not. We cannot say that it will work for high-dimensional problem in a reasonable computing time. We don't know yet, but you should know that the problem of finding reliable approximation of attractor is already a difficult problem for two-dimensional problems. Even if you have any other method to work for this simple problem, or this one, able to find an enclosure of attractor, maybe there exists, but no general method are able to me to find attractor or even such simple problem. Okay? Okay, so I propose to stop for today because now what I suggested to go with your computer, I will maybe help you to install IBEX, interval library, and so on. So I'm here also tomorrow for people who want to install different computer tools related to internet.
Cool. So do you want to install here or do you want to go to
As you wish, it depends of Alexandro. Yes.
do you prefer that we stay here for install the program operative or go to the meeting room in, in control center?
E1, yeah. I
Which
think,
one do you-
no, I think it's better in E1, no? Or,
Yes, yes.
which is
Possible.
big.
Yes, I will.
We can stay. So, shall we stay here? Or?
I'm fine.
I don't know, it's up to you. It's,
If you want to install programs and okay,
Yeah, let's stay.
that's
it's okay. Okay, let's go.
Yeah,
But then you'll have the graph.
No, no, to me squares are not enough.
Well,
Polygons.
but the thing is, you won't know which polygon to choose.
No, no, all
So
models are
yeah, it's
possible.
different.
There is some possibilities.
I mean, to make it automatic,
No, no, yes, to do mathematics.
so then your resolution will depend on the size of the square.
Yes, yes, yes. No, no, no. What is important? The intuition to make everything automatic. If you have a vector field, imagine I have a box. If my vector field is like this, for instance, so when I small enough, we can say that all of them have a good direction. It is, I can, if I bisect like this, it's good. Because I can show that I cannot have this relation. Good information. Now, there is some boxes where it will turn like this. Always some boxes where it will turn. So for this type of situation, if you bisect like this is not good. If you bisect like this, it can be good, but sometimes you will have also to bisect like this. Otherwise, you will obtain only boxes like this, and you will want to bisect again like this, whereas the vector field is like this. So for such a situation, to me, I think it's better to choose something like this, so that you will have no relation between this one and this one. To me, it's better to use polygons for this type of problem. With square, it will not work because of the region where the vector field is. But maybe there is better. I don't know. Maybe we can take to avoid this kind of problem where the arrows are either vertical or horizontal. Maybe it's better to consider two frames, one like this and one like this. So the singularity that will appear in one frame will not appear in the other frame. Everything has to be imagined. Okay?
Yeah.
So we go down? We go down?
No, I think, oh.
Yeah, I must leave.
Or so we can stay here as you wish.
No, no, but he must do
However, I've got several questions about optimization problem.
Ah yes, I did not speak about optimization problem yet, but well,
Yeah. During my bachelor thesis, I implemented library for automatic differentiation methods.
automatic differentiation.
Yeah,
Yes,
using interval analysis.
yes.
And now, actually, I'm working on global optimization and some extensions
Ah okay.
while I write global optimizations.
Okay, so you are working with interval analysis,
Yeah,
and you are in this university?
from Warsaw University of Technology. However, in January I started
Oh.
computer science here.
Okay, okay, that's good.
I'm very keen to apply automatic differentiation to an intervals to global optimization.
Yes.
However, on GPU, on CUDA.
Ah okay, 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 okay. That's good.
Yeah.
Yes, 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 yes.
Because this problem is very efficient to parallelize
Yes.
on GPU, and
it.
I would like to discuss.
Ah yes, okay.
with
So
you.
when now, as you wish, maybe. So what we can do? Maybe you can tell them to implement the. We will parallelize. We'll parallelize. Maybe you can show them how to install Qt. Okay. And then you have Wi-Fi here.
Yes.
Okay, and then at least the same example as we made this morning. It's
Yeah.
possible?
Yeah.
Okay.
Okay.
But tomorrow if you want to see where we can find you.
I will be here.
Here.
Yeah, more or less. Depends because tomorrow E1 is not free all
Okay.
day, so maybe send me an email
Okay,
when you.
very good.
We have to find a room.
Yeah.
Okay, that's
Yeah.
good.
Send me an email before.
Okay, so can we back?
Yes, yes, no problem.
Okay, can I take?
Yes, of course.
This page.
So I hope that you are familiar with automatic differentiation methods.
Yes.
I implemented these methods in GPU and CUDA.
So it's symbolic, pure symbolic.
Yeah.
So you don't need parallelism for that.
Home page, yeah.
For the gradient and the S matrix.
And the
For the
Mission
evaluation of
matrix.
the gradient and the
Yes.
S matrix.
Yes.
I hope that it will be might be an option
And
to
here.
robotics as well.
Why do you need parallelism for that? Because most of the time it's nice to use the GPU for working with intervals,
Yeah.
not for symbolic. I think it doesn't take a lot of time to compute the derivative, the symbolic derivative.
Symbolic. Yeah. Exactly.
Yes, yes, yes.
Yes. However, for example, for finance,
Yes.
where we have to evaluate, for example, the hedge parameters, the risks for some financial models.
Yes.
And you have to evaluate it. It's not.
Yeah. Exact derivatives.
Yes, but you want
You
to
don't evaluate them.
or you want
Evaluate.
to compute the syntax tree, for
It's
instance, or
creator.
usually the automatic differential equation. You give them a C++ code,
Yeah.
and they will give you back the C++ code of the derivative.
Yeah.
That's what you are saying.
The adjunct methods. The adjunct methods.